So let's keep going here. So last week we had started talking about chemical compounds. We introduced these chemical formulas like CO2. All right, and really we talked about the types of bonds and naming these compounds. We're going to do a little bit more about how we quantify these things. Importantly, very essential towards like early chemistry. Really what happened at the turn of the scientific revolution was to really start to quantify our sciences way more than they had been doing. There was a real qualitative approach to science for a very long time, and they started being like, no, we need to put numbers and measurements on that. And that was really when the foundation of this theory of an atom, or rather matter being made up of atoms, came from. And it came from one of these very early observations about these ratios of different atoms being locked in. So for example, if I had a sample of carbon dioxide, it doesn't matter if it was a big sample or a small sample, there was always twice as many oxygen atoms as there were carbon atoms. And that like perfect ratio was one of these things that clued in that we must be talking about atoms. Okay. So in chemistry, we like to talk about atoms, but if we were talking about how many individual atoms there were in a sample, it would be a really obnoxiously large number to be working with. Okay? So instead, in chemistry, and this is a unit that's very specific to chemistry, we use something called the mole. All right, the mole is giving us the amount of atoms or molecules that we have present. Okay, so when you hear this measurement, 3 moles, really it's telling you how many atoms or molecules you have in that sample. All right, the definition of a mole . 1 mole is equal to 6.0221 times 10 to the 23 of whatever it is that you're talking about. And for right now, I'm just going to use this catch-all term particles. All right, we'll explore that a little bit more. So if I have a mole of a substance, so is 6.0221 times 10 to the 23 a big number or a little number? Big number. It's like an incomprehensibly large number. 10 to the 23 is a ridiculous amount of zeros to be tacking on to the end of a number here. All right? And yet this bottle here probably contains about 4 or 5 moles of water. So that's why we like to use this quantity of the moles. We don't want to have to talk about some ridiculously large number of atoms or molecules present. Instead, we're going to use this shorthand unit, the mole. Okay? In order to better understand what a mole is, I feel like it's best to understand through analogy. All right? And this analogy would be the phrase a dozen. All right, a dozen, the definition, would be 1 dozen equals what? 12 of whatever it is you're talking about. So for example, if I said that I had 1 dozen eggs, you know that I have how many eggs? 12 eggs. All right, just like if I were to say I had a mole of helium, you would know that I had 6.0221 times 10 to the 23 helium atoms. What's up?
Does that mean that has unlimited significance?
What does? Sorry.
6.0226.
No, it does not, because it is such an incomprehensibly large number that this does go for quite a few more. This is sig fig limited. It's not an exact conversion. Okay, and likewise, let's say that I had 2 dozen cookies. You know that I would have how many? 24, right? And so in the same way, I don't have to just have a mole of atoms. I could have 2 moles, or 3.5 moles, or 0.69 moles, whatever it might be, right? So first thing that we're going to learn how to do is use our mole definition as a conversion factor. Right, so mole as a conversion factor. Okay, I'm going to leave, and let's just start with our definition here. I'm going to leave a little bit of room for some notes here, and let's just put down a working example. Let's say that I have 4.65 moles of helium, and I want to know how many helium atoms I have. All right, what you're going to see is this looks a lot like the exact same kind of what's called dimensional analysis, the unit conversion kind of math that we were doing previously. This is going to be the exact same game. All right, if we remember, if we go back to our constants page, okay, and I wanted to convert inches into centimeters, what I did was I took this relationship here, 1 inch is equal to 2.54 centimeters, and I turned it into a conversion factor, right? Where I had one side of that equality stacked on the other, and this allowed me to cancel my units out and leave me with the units that I wanted. Right? We're going to play that exact same game now, but now we have a different conversion factor. Now we have this mole to particle conversion factor. All right? First of all, let me clarify this word particles, because here it says atoms, here it says particles. What's going on here? All right, so first of all, let's make a little aside here. This term particle is really just a catch-all term for anything small. So you could say atoms are particles, you could say molecules are particles, we have dust particles, electrons are particles. Particles is just a catch-all term for something that's teeny tiny small. All right? Now, in chemistry, we're going to be more specific often, and it's going to depend on context. So instead of particle, you may see if we're talking about individual atoms, then it would ask you for how many atoms you have. And you would still use this exact same equality here, but instead of particles, you'd be converting into atoms. All right? This is if we were talking about a single element. If we were talking about a covalent compound, we call those molecules. We also have this term that we use for ionic compounds. For ionic compounds, we shouldn't be using the word molecules. Molecule is specific to covalent compounds. For ionic compounds, we call it a formula unit. Right? So NaCl wouldn't be a molecule, it would be a formula unit. And so you could see any of these four terms in your problem, all of which should be a big clue that you're going to be using this conversion factor here. All right, and I just kind of already gave it away, so let me clarify. This number over here, 6.0221 times 10 to the 23, this is what we call Avogadro's number. Avogadro, very famous 17th century scientist, very early chemist. Okay, so in order to do this problem here, I need a conversion factor. I need to convert from moles into atoms, and I'm going to use my Avogadro's number conversion factor here to do it. And just like before, when we had 1 inch equals 2.54 centimeters, and we stacked one side on the other, we're going to do the exact same thing here. I'm going to say that this is 1 mole over 6.0221 times 10 to the 23. In this case, we'll use that term that we're using, atoms. Okay, one more thing, I want to be lazy here. We have a way that we simplify moles. So similar to how we simplify or abbreviate grams using that lowercase g, we have a simplification or an abbreviation for mole, and they really didn't save us much writing at all. It's MOL instead of MOLE. All right, so MOL is our units of moles. Okay, and just like any of our conversion factors, I could use it as is, or what could I do with it? Flip it. Take that 6.0221 times 10 to the 23 atoms over 1 mole. All right, so given these two conversion factors that we built here, everybody take a second and see if you can't convert from 4.65 moles of helium into helium atoms. All right, so first of all, I'm starting out with 4.65 moles of helium. So which one of these two conversion factors am I going to use? The one on the left or the one on the right? The right, because I need moles on the bottom. So if I set it up here with my mole of helium on the bottom, my 6.0221 times 10 to the 23 helium atoms, then moles will cancel out, and I'll be left with those units of atoms. All right. Cool. So punch that into my calculator. All right, and I will say, if you are having trouble figuring out how to enter numbers into in scientific notation in your calculator, please let me know. Come to me at the end of class, and I can show you. All right, but punching this in, we get 2.80027 and a bunch of change times 10 to the 24th. All right, so everybody look, your calculator should have given you this answer in scientific notation. It's either going to say times 10 to some exponent, or it could give you that capital E. We talked about how that capital E means times 10 to the, but just note that the answer it gave you is in scientific notation here. And as we said, our units, atoms. All right, and then what's my last step? Significant figures. All right, so my first measurement here had 3 sig figs. And yes, as noted, our Avogadro's number is not an exact quantity. All right, so Avogadro's number here usually doesn't limit us. It has a bunch of them, but nonetheless, we need to be good and look. But I'm going to round my final answer here to these 3 significant figures. Okay? So when I'm doing that in scientific notation, importantly, this would become 2.80, but I also have to keep the times 10 to the 24. 2.8 and 2.8 times 10 to the 24 are very different numbers, right? So we want to make sure we keep that times 10 to the business on there, put our units of atoms, put a box around it, final answer. Okay? All right, so then I want you all to try to do one on your own here. If I had 3.99 times 10 to the 21 H2O molecules, how many moles of water would I have? All right, so this time I'm going to have to divide by Avogadro's number, divide by that 6.0221 times 10 to the 23. Before we actually punch this into our calculator, if you remember at the beginning, I told you the difference between people who are really good at chemistry versus people who are just good is being able to look at your answer at the end and see if it makes sense, right? Make sure that you can check and be like, okay, that's the number that I would expect here. So looking at this number here, 3.99 times 10 to the 21, does that mean that I have more or less than 1 mole of water? Less, because 10 to the 21 is less than 10 to the 23. So my answer should be less than a mole of water, right? So just a little bit of a sanity check here. And I want to point this out because sometimes people will get a crazy large answer, like one that's something times 10 to the 40 something, all right? And that just means that you messed up your order of operations. So first of all, if we did this correct, we should get 0.0066255. And we're talking about moles of water. If I round this to my 3 significant figures here, that would be 0.00663 moles. Okay? So if you instead got some ridiculously large number, the problem again is order of operations. We need to make sure to divide by not just the 6.0221, but also the times 10 to the 23. Which means that when we punch this into our calculator, we need to put this in parentheses so that both of those stay underneath that numerator. All right? Otherwise, you're dividing by 6.0221, but then multiplying everything by the 10 to the 23. We need 10 to the 23 to be under this divisor sign here. All right? So again, order of operations, when you're dividing by a number in scientific notation, you're going to have to put it in parentheses when you type it into your calculator. Put a box around it, final answer. Cool. All right, awesome. So what you're going to see is, especially when we start talking about chemical reactions, we're going to default to this unit of moles. And really, when we're talking about how many moles of molecules or atoms that we have, really that's just a stand-in for how many individual atoms or molecules, all right? However, if we look around this room, unfortunately, there's no such thing as a mole counting machine. If there was, we would just always use moles. Unfortunately, they don't exist. So what we have in order to measure out a certain amount of substance is our mass balances here. All right, so we need to be able to convert from mass to moles or moles to mass. That's going to be the name of the game. Mass being what we practically work with in the lab, moles being how we're going to talk about how much chemical reaction has actually occurred. All right, so this is going to introduce now molar mass. Molar mass, by definition, is the mass of 1 mole of a substance. All right, practically speaking, what molar mass is going to be doing for us is it's going to help us convert from mass into moles or vice versa. All right, so if we go to our periodic table here, let's just go, I'm going to go grab an element. Let's do carbon. Okay. This number on the periodic table, so for carbon it's 12.011. We called this the atomic mass or the average atomic mass, and it is. It's the average, the weighted average of all the carbon isotopes that exist. But they very cleverly defined these average atomic masses to be equivalent to what we call the molar mass. So the molar mass of carbon, all right, let's just say molar mass of carbon is this 12.001 011. And our units for molar mass are grams per mole. All right, this is an important sticking point. It's not just grams, it's not just moles, it's grams per mole. That's what that number means. And so we're just going to highlight and make a note so we don't forget. This is always the units for molar mass. Okay, so that means if I have a mole of carbon and I go and I count out 6.022 times 10 to the 23 carbon atoms and I go and throw them on the balance, that balance will read 12.011 grams, right? That's our molar mass. But again, what it's going to be most convenient to be used for is as a conversion factor to help us to convert from mass to moles and moles to mass. So what we're going to do is take this mixed unit quantity here. We were playing this game with density in our first week, right? Density was another mixed unit quantity of grams per mil. This one's grams per mole, but we're going to treat it the same way. Turn it into a conversion factor by putting that 12.011 grams over 1 mole. All right, so this is how we turn our molar mass into a conversion factor. All right, and just like all my conversion factors, I could use it as is or flip it, all right, depending on what my units are telling me to do. So let's just go ahead and utilize this as a conversion factor. Let's say that we had 7.3 moles of carbon. What would be the mass of that carbon? All right, we'll do this one together here. I would start with my 7.3 moles. Okay, now I'm going to take this molar mass and I'm going to multiply so that moles are on the bottom and the units that I want, the grams, are on top. All right, punch this into my calculator, 7.3 times 12.011. Okay, turns out that my mass here would be 87.6803. And those units, moles, cancel out, leaving me with units of grams. All right, now because this is a chemistry class, we have that last pain in the butt step that we got to do. We got our calculation, we got our units. Next we need sig figs. All right, so my 7.3 has 2 sig figs. But what about molar masses? Okay. Importantly, molar masses are measured quantities. Strictly speaking, molar masses are not exact. They have sig figs associated with them. However, it's such a pain in the butt trying to keep track of molar mass sig figs, especially when we start adding them together to make compounds. So I'm going to make y'all a deal. As long as you always use every digit from the periodic table, we can pretend like these molar masses are exact. All right, so for the purposes of our sig figs, just to make our lives a lot easier, we're going to pretend like molar masses are exact and won't be limiting our sig figs. Usually they don't anyway, because they have a ton of digits on them, but in the rare case where it would, we're going to pretend it's exact. So best case scenario, we're not going to be limited by that molar mass. So my final answer here would be this 88 grams of carbon. So if I had 7.3 moles, put it on the balance, I would have 88 grams. Okay? All right, I'm going to put two more up for y'all to do on your own here. Yeah. Oh, hold up. Let me fix this second one. That is a ridiculous number. There we go. Can't really have 8.165 atoms. right, so for this first one here, I got my 15.7 grams of neon and I divided it by 20.179. Where did this number come from? Periodic table, all right? That's my molar mass of neon. That gets me from grams into moles, and then rounding that to my 3 sig figs, I get 0.778 moles of neon. In terms of strategy, so obviously I just introduced molar mass. The section's labeled molar mass. It was a pretty good clue that we were going to need a molar mass, right? But it's not going to always have that context clue. So if I'm just reading a problem, how am I supposed to know, oh, I'm going to need a molar mass for this particular problem? Well, molar mass is importantly the only way that we can jump from grams to moles and moles to grams, right? So anytime I see a problem that has both grams and moles, in my mind, I'm immediately thinking molar mass. All right, you see those two units in a problem, you're thinking molar mass. That's how you're gonna have to do it, okay? So then thinking here, now I'm starting in atoms and trying to get to grams. So how am I gonna do that? I'm not just gonna be able to make one jump from atoms into grams. I'm gonna have to think about this a little bit more carefully. First of all, context clues. This word atom is a big clue. All right, there's only one way that we know how to deal with individual atoms, right, from a conversion factor standpoint. And that is what? What's our conversion factor that helps us jump from atoms into something else? Avogadro's number, right? So again, in terms of strategy, I see this word atoms, and I'm immediately thinking I need Avogadro's number. Okay. Avogadro's number, that will help us get from atoms into what? Moles. And now I see grams and moles in the same problem here. And when I see grams and moles together, I'm thinking molar mass. All right, so whereas Avogadro's number is going to help us get from atoms to moles, we can make that jump from moles to grams using our molar mass. All right, so we have our 8.165 times 10 to the 24 atoms. Divide that by Avogadro's number. And then I'm going to need to multiply by that molar mass for iron. Iron has a molar mass of 55.845 grams in 1 mole. Okay, punch this into my calculator here. I get 757.168 and some change. And my units here, atoms cancel out, moles cancel out, and I'm left in units of grams. Okay, and then lastly, I'm going to round this to 4 significant figures. So my final answer here would be 757.2 grams of iron. All right, stringing together now 2 of those conversion factors that we learned here. Cool. Okay, so that's great if we're talking about individual elements. Then we just look on the periodic table for those molar masses. All right, but what about the molar mass of a chemical compound? All right, so first of all, if I had 1 molecule of CO2, that would imply I had how many carbon atoms and how many oxygen atoms? I got 1 molecule of CO2. How many carbon atoms am I holding? Just 1. And how many oxygen atoms am I holding? 2. All right, again, these are locked in by my chemical formula here. That's what it means to be carbon dioxide, is to have one carbon for every 2 oxygens. Okay, so now let's say that I had a dozen molecules of carbon dioxide. That means I have how many carbon atoms? 12, but if I was to use that unit dozen instead, how many dozens of carbon atoms would I have? 1. And how many dozen oxygen atoms would I have? 2. Okay, so now let's use the incomprehensibly large mole. If I had a mole of carbon dioxide, how many moles of carbon would I have? Just 1. If I had 6.0221 times 10 to the 23 carbon dioxide molecules, that means I would have 6.0221 times 10 to the 23 carbon atoms. And how many moles of oxygen would I have? 2. All right, a mole of carbon dioxide, each carbon dioxide containing 2. That means I would have 2 moles of oxygen. Remember, mole and dozen, directly analogous. All right, I understand that a dozen is 12, and we can all wrap our head around that number. And 6.0221 times 10 to the 23 seems like some made-up bizarro world number because it's just so huge. But again, directly analogous to one another. So, fortunately for us, because a mole of a chemical compound always just contains a certain number of moles of each element, and those are locked in by the chemical formula, we get to use a very simple way of calculating our molar masses. All right, fortunately for us, masses are perfectly additive. All right, so first of all, I'm going to use mmCO2 for the molar mass of CO2. All right, and again, masses are perfectly additive. It turns out that if you had 1 gram of carbon and 1 gram of nitrogen, and you put them both on the balance, it would be exactly 2 grams. Okay? That's not the same for all quantities. Volume, for example, is not additive. If I took a liter of water and a liter of alcohol and I mixed those together, I would not have 2 liters of liquid. It would be pretty close, but it would not be exactly 2 liters. All right? The volume that atoms take up is not something that's conserved, but the mass of atoms is. It's perfectly additive. So if I want the molar mass of carbon dioxide, that would be the molar mass of my 1 carbon plus 2 times the molar mass of oxygen. All right, that's because I have 1 mole of carbon and 2 moles of oxygen in that mole of CO2. All right, and this is where you can see if I was going to make you keep track of sig figs, it would be such a pain in the butt because now we got a mixture of multiplication and addition going on in there, and that's why we're going to just pretend like they're exact here. I'm going to just take my 12.011 grams per mole, and I'm going to add 2 times oxygens, 15.9994 grams per mole. All right, and again, the deal is you don't have to worry about sig figs. You do have to take every number from the periodic table. So oxygen, 15.9994 is very close to 16. It is not 16. You're not just going to round it. You're always going to take all the digits that our periodic table gave us. Some scientists worked very hard to get those 4 decimal points on the mass of oxygen, so we're going to keep them. All right, so punch this into our calculator. The molar mass of carbon dioxide is 44.098 grams per mole. All right, so let's just utilize our new compound molar masses here. Okay. Let's say that I had, what do I want to do, 15.4 grams of water. And I want you to tell me how many moles of water. All right, so step one, I had to figure out what the molar mass of my compound was, what the molar mass of water is. I did 2 times the molar mass of hydrogen plus the molar mass of oxygen to give me 18.0152. And again, the units, as always, for molar masses are grams per mole. So then I'm going to take my 15.4 grams and I'm going to divide by that molar mass, divide by the 18.0152 grams, put that under the 1 mole, and we get 0.8548. All right, our units here, grams cancel out, and I'm left with units of moles, and then we'll finally round this to 3 significant figures. So 0.855 moles. Cool. So given any chemical formula here, H2O, for example, CO2 is what we did previously. We can figure out its molar mass from that chemical formula and then use that molar mass to convert from grams to moles or moles to grams, just like we were doing for individual elements. Cool. All right, one last thing we're going to learn here today, a last conversion factor, or we can treat it like a conversion factor, is what's called a mole ratio. Okay, And this is going to be this conversion factor that helps us convert from atoms into compounds or vice versa. All right, so what do I mean by that? I'm going to leave a little bit of room here for some notes, but I just want to put down an example of what I'm trying to accomplish here. We're going to, if I had 4.3 moles of SCl5, I want to know how many moles of just chlorine there are. All right, and our little conversion factor that we're going to build to do it is what we call a mole ratio. Okay, so let's take this formula here, SCl5, and since there are two distinct elements in this compound, I could actually build two different conversion factors, two different mole ratios. So one would be my conversion factor looking at sulfur, and the other one would be my conversion factor if I was trying to figure out how many chlorines there were. All right, so according to my chemical formula here, if I have 1 mole of sulfur pentachloride, how many moles of sulfur would there be? I have 1 mole of this, 6.0221 times 10 to the 23 of these molecules. How many sulfurs do I have? I have 1 mole, all right? And where does that 1 come from? Just simply from our chemical formula here. All right, so then if I had 1 mole of sulfur pentachloride, how many moles of chlorine would I have? 5, right? And again, just from my chemical formula. Okay, so depending on which element I'm talking about, I could figure out how much sulfur I had or how much chlorine I had, how to convert from those individual atoms into our chemical compound. All right, so let's take our 4.3 moles, and now I'm going to be good to not just include the unit, but also include who I'm talking about. All right, so I'm not just going to say 4.3 moles, I'm going to specifically say this is 4.3 moles of sulfur pentachloride. Right, and now I'm going to multiply. I know that 1 mole of SCl5 contains 5 moles of chlorine. And notice that this works just like all of our other conversion factors. Our units cancel out. We're left with those units that we want. All right, I'm trying to get rid of moles SCl5 and be left with moles of just chlorine. Okay, my calculator spits out 21.5 moles of chlorine, and now it's trying to do our sig figs. Time to do our sig figs. All right, 4.3 moles has how many sig figs? 2 sig figs. So then what about these mole ratios here? All right, mole ratios are always going to be exact quantities. That number, 5, there is exactly 5 chlorines per sulfur. It's not like sometimes there's 5.1, other times there's 4.9. So mole ratios are always exact, meaning not going to limit my sig figs. I'm going to round to those 2 sig figs, or 22 moles of chlorine. All right, so last step, last conversion factor that we're going to learn today are these mole ratios here. They allow us to convert from individual atoms into compounds or vice versa. As we did here, we converted from moles of our sulfur pentachloride, our compound, into moles of just those individual chlorine atoms. All right, So I'm going to put down a few examples to wrap this up here. Okay, whoops. Where do we go? right, so I'm going to kind of quietly fill in my work up here so you can look up and check, or if you're stuck, see where your issue is. All right, so looking up at this first one here, I'm gonna make a little bit of room so we can sort of talk strategy here. Okay, so first of all, I'm looking at my problem here and I see this keyword molecules, and when I see molecules, I'm immediately thinking Avogadro's number. Yes, Avogadro's number. Absolutely. That's how we know how to deal with molecules, atoms, formula units. All of those tell us Avogadro's number. And Avogadro's number would then put us in moles, but we would be specifically in moles of our compound, SCl5. Right? If we're starting out in SCl5 molecules, using Avogadro's number takes us to moles of our compound. But I want to figure out how many moles of just chlorine I have. So that's how I know I'm going to need to use that mole ratio. All right, and so my mole ratio here will allow me to convert from moles SCl5 to moles of just chlorine. And as we said before, there are 5 moles of chlorine for every 1 mole of our compound. Let's punch this into our calculator here. We're going to round this off to 3 sig figs. One of the things that I should have made note of here that I just want to clarify, your units here, when you're going to actually put this answer in your homework, your units are units of moles. The chlorine is helpful to leave on here for you to know who you're talking about, but you can't enter the chemical formula in. It's technically not part of the units. All right, so I would just type in 0.519 moles. So same up here. Let me be good. Final answer here. I'll leave the chlorine on to remind me, but really it's 22 moles. So down here, 0.519 moles. Okay, so here, same idea. Strategy-wise, we see grams and moles. So now we're going to need to use our molar mass. Since I'm starting out with grams of water, I'm going to have to use my molar mass of water, that 18.0152 grams per mole. We calculated that previously. And that will give me in units of moles of my compound, moles of water. So in order to figure out moles of individual hydrogen, I'm again going to have to use that mole ratio. That'll allow me to jump from my compound into my individual atoms. All right, so again, rounding that off to the correct number of sig figs, 1.628 moles of my hydrogen. All right, and this one, now we're starting with grams of oxygen, and we're going to try to go all the way to carbon dioxide molecules. All right, if we're going to sort of map this out here, we know one way to get to molecules, and that's using what? Avogadro's number. All right, so if we used Avogadro's number, then we can get to molecules of carbon dioxide. But what would we have started with units-wise in order to get to molecules? What units would I have to be in here to use Avogadro's number to jump into molecules? Moles. And specifically, if I'm going to use Avogadro's number, that means I would need moles of carbon dioxide. But I'm starting myself out not in CO2, but just oxygen. So how am I going to make this jump from moles of oxygen into moles of carbon dioxide? Our mole ratio. All right, and then I'm starting in grams of oxygen. No, I'm going to get to moles of oxygen. How do we get from grams to moles or moles to grams? Molar mass. So this will string together all three of these terms that we learned how to use today, our molar masses, our mole ratios, and Avogadro's number. All right, starting this out, we have our 5.93 grams of oxygen. I'm going to need the molar mass. The molar mass of what? Oxygen or carbon dioxide here? Just oxygen. I have grams of oxygen. I can't be dividing by grams of carbon dioxide. That's not going to cancel out. So I need that 15.9994 value I get for my periodic table. That'll allow me to convert from grams of oxygen into moles of oxygen. All right, now I can take, now that I'm in moles oxygen, I can use my mole ratio. All right, I'm going to need moles oxygen down here on the bottom and moles CO2 on the top. So what value am I going to put down here on the bottom? The 2 moles of oxygen for every 1 mole of carbon dioxide. This is inverted from what we had seen previously. And now we're going to use the fact that if we had 1 mole of CO2, we know there would be 6.0221 times 10 to the 23 CO2 molecules. All right, so punching all that into our calculator. We get 1.1160 times 10 to the 23 molecules of carbon dioxide. All right, rounding that to our correct number of sig figs. My original measurement here has 3. Molar masses, we said we're going to pretend are exact. Mole ratios are actually exact. We do got to consider these 5 sig figs in our Avogadro's number, but my fewest number here is 3. So my final answer being 1.12 times 10 to the 23 molecules of carbon dioxide. And again, that last example there utilized all 3 of these conversion factors that we learned how to build today. Cool. All right, we're going to call it there. Okay. If you were having trouble with your calculator, please come up and see me and let me show